Sir,
Yuvraj.
Present, sir.
Okay, there are two absentees, Vikas, Arunachalam. Okay, quick information. Coming Saturday is your quiz 2. Right, so I have already announced the syllabus that you need to go through for the quiz. So you have two chapters. Chapter number 3, which is about SI engine combustion and CA engine combustion. Chapter number 4, which is about combustion instrumentation. Okay, so these two chapters you need to go through. Okay, and come prepared for the exam. You can have your calculator with you. Okay, similar to quiz 1 exam, you can bring the calculator. Answer sheets, everything will be provided to you. Okay. So the procedure is same, and the exam venue is also same. We will have coming Saturday. For the people who are taking exam online, the procedure is again the same. Whatever we followed last time, the same thing will be followed. I will send you the question paper just before the exam. Okay, and you are supposed to scan your answer script and send it to me to the email ID from where you receive the question paper. Okay, after I confirm receiving your answer scripts, you can log off. Until then, you are supposed to be login. Okay, I will send the meeting link before the exam. And yeah, so are there any questions related to the quiz? If you have any doubt, you can write to me. I will get back to you. Are there any questions you have about the exam? Exam will be for 30 minutes, same 50 minutes duration. So I have already discussed with you enough about keeping the time. Okay, so I hope you will follow what we have discussed earlier. And I don't think you will have a problem of shortage of time this time.
Sir, on the fourth chapter, for the problems, if possible, will you be in a position to share us some reference problems so that we can...
Reference problem is exactly same as your assignment, whatever given in the assignment.
On the chapter 4, sir?
Chapter 4, there are no problems.
Okay.
Chapter 3, only in SI engine combustion, whatever model problem you have attended in the assignment, similar kind of problem you can expect. The rest of the questions are theory questions, basically to check the concepts. Theory questions are mean for checking the concepts, and you are supposed to answer it briefly. This is what I said last time also, to save some time. I will just check whether you got the concepts correctly. The way you write the answer, you have to briefly convey answer up to the point, and I will check whether you understood the concept through the question. So you can convey it as briefly as possible to avoid running out of time. Okay.
Thank you.
Thank you so much, sir.
Yeah, okay. Okay, come prepared this time. Okay, do well. I expect a better performance compared to this one. Okay.
Sure, sir. Sir, Professor, sir, just I joined just now.
Yeah, I will note down. You have already sent an email also, so I will mark attendance.
Okay, sir.
So I have received all of your assignment except one. I have already wrote an email. Okay, please take care. The due date is over already. Okay, please take care. Please note that if you don't submit the assignment marks cannot be given. So weightage for assignment is 10% for your grades. Meaning that 5% weightage will be for assignment 1 and another 5% weightage for assignment 2. If you don't submit the assignment, you are actually losing those 5 marks. 5, or if you don't submit both assignment, 10 marks you are losing. Okay. So you should not get into that situation. So I have given enough time. Please see that all of you have submitted the assignment. Okay. Okay, so welcome back. So we are here in chapter 5. We are now discussing the second module, emission module. In the emission module, the first chapter is about pollutant formation in SI and CI engine and factors affecting emissions. So here, previously in the previous couple of classes, we discussed about the types of pollutants and what health effects the pollutants create on the human being. This is the reason why they are designated as pollutant, because they create several health effects. Some of them are fatal, as we have discussed in the previous class. So that's why these species, some of the species emitted from the IC engine due to the combustion event. Okay, these species are the products of combustion. Okay, since you are combusting fuel and air, you get into these species in the engine tailpipe or exhaust pipe. And since they have a fatal effect on the human health, we need to closely monitor the concentration of these species. That's why we have legal mandates, emission mandates. Okay, and the concentration of pollutants, of course, are now almost zero level. If you look at the current BS6 norms, so we are moving towards zero emission. Although there is a combustion we are trying to control, please note that combustion products are many more. Our focus is on in these four, because these four species are creating health effects. Okay, in future you can also expect some other species to be included. For example, CO2. CO2 is an important species to be included because they don't have immediate effect, CO2 or any other species. Okay, apart from these four, they have some long-term effects. For example, now all of you are familiar with what effect CO2 create. Okay, so you could see drastic variation, seasonal variations in the rainfall as well as in the summer and winter. Okay, there are drastic changes in the right weather conditions. So these are some of the effects of these species like CO2 being discharged into atmosphere. Always there is a threshold limit. That's what I say. For even for health effects, there is a threshold limit. Once if it crosses that limit, then we will get into the problem. So that's why we cannot take risk. We need to keep a high factor of safety, since we cannot compromise health. Okay, so that's why we have to monitor and control. A quick summary of pollutant types. So here this slide shows a quick summary of pollutant types. Fuel, we are dealing with our hydrocarbon fuel. I already said that carbon content is around 84%. Hydrogen content is around 14%. Okay, so the fuel we handle are gasoline and diesel or hydrocarbon fuel. They contain primarily carbon and hydrogen. Apart from this, there is a sulfur to a minimum level. According to the current BS6 norms, sulfur in gasoline is nothing. Sulfur will be there in diesel, but negligible concentration. The current BS6 fuel norm, like emission norm, you have a fuel norm, right? BS6 fuel is having only 10 ppm of sulfur. We call it as ultra low sulfur diesel. Okay, so this ultra low sulfur diesel is not going to create any major effect in terms of pollutant emission. So SOx is a resultant of sulfur combustion. Okay, so these levels are very low because we are controlling sulfur content to up to 10 ppm, right, which is nothing. Then you will have other component in the fuel. This is an additive. Based on what additive you use in the fuel, you will have some other component other than hydrogen and carbon. For example, here I have given lead. Lead was earlier used as an anti-knock improver additive. Oh, you know that, okay, but lead is poisonous. So if you combust lead, it leads to lead oxide. You cannot let out lead oxide into surrounding ambient because it's a poisonous gas. That's why this is avoided, but this is just a representative compound to show that if you have any additive added to the fuel, that also undergoes combustion and produces several products. Okay, so you should also keep an eye on or keep a check on what additive you use and combust. Whatever you combust is going to release its products into surrounding ambience. So we combust fuel with the air, not with pure oxygen. For combustion, you need oxygen. But oxygen, pure oxygen is expensive. I think already we discussed about that. We use air because it's freely available. When the vehicle moves in, like we are inhaling air, vehicle also inhale air, okay, and takes in air. It's freely available, okay, through its induction system, suction system. It takes in air into the engine. Fuel combusts with air and releases various products. The products shown on the left side are ideal combustion products. So for example, carbon present in the fuel If at all it undergoes complete combustion, it produces CO2. Hydrogen present in the fuel, if it completely combusts, it forms H2O. Okay, so complete combustion of carbon and hydrogen forms CO2, H2O. And if the temperatures are less, nitrogen in the air will come out as it is without oxidizing. So, and then if you use excess air, you will have oxygen. So the ideal combustion products are CO2, H2O, N2, and O2. If these products are emitted, there is no problem on the human health. Okay, but what engine emits through the tailpipe is there are several other species as indicated here. The one circled with the red bubble are the primary pollutants or regulated pollutants. So we already discussed the health effects of these 4 species. CO is toxic gas, and HC, some of the species. HC is multi-component, more than 100 species, as I said. Some of the hydrocarbon species are carcinogenic. For example, benzene, butadiene, they are called designated as air toxics. Okay, generally their levels are low, but if you have a large vehicle population, which is quite common in the city, right? You could imagine the number of vehicles, okay, on-road vehicles, right, moving every day. So you can imagine the concentration of the species, this species emitted into surrounding ambience from this vehicle. There's a large vehicle population, vehicle density is very high, especially in the city. So you have a larger concentration of this species being emitted into surrounding ambience. Some of them are air toxics in HC, and PM, you have soot, you have other species, liquid and gas phase species put together is particulate matter. Okay, and CO primarily is formed due to partial combustion or partial oxidation. You know, combustion is an oxidation reaction. Partial oxidation of carbon leads to CO. If at all CO is completely oxidized, it leads to CO2. But partial oxidation is quite possible in IC engine. Okay, so we already discussed about the concentration of CO from SI and CA engine. In SI, it's very high, typically 200 grams for every kg of fuel that is burned. Okay, so you have partial oxidation leading to CO formation, and partial oxidation also forms SC. For HC, there are 2 sources. One is partial oxidation, and the other one is misfire or incomplete combustion. When the engine misfires, you can expect the fuel coming out as it is. So those are the HC species being emitted through the tailpipe. And then you have particulate matter. The major component is soot. Soot comes from when there is a misfire, you will have fuel, you will have unburnt fuel coming out. Okay, unburnt fuel is also included in the particulate matter because soot carries, as I said, soot provides a surface for carrying the unburnt fuel. Okay, soot is a solid carbon that is formed from rich mixture, we have already discussed, and soot carries unburnt fuel. So incomplete combustion will also increase the levels of PM, especially the unburnt fuel carried away by the soot. Then you have NOx. For NOx, the fuel is not the source. Fuel doesn't have nitrogen, fuel doesn't have oxygen. The source for forming NOx, NO1, NO2 is air. You could see that air contains both nitrogen and oxygen, which is what is forming this NOx. Okay, oxidation of nitrogen is what is leading to NOx, formation of NOx. So oxidation of nitrogen, we generally refer this as a combustion byproduct. It's not a primary product, it's a byproduct. Okay, primary products are carbon and hydrogen oxidized products are primary products. This is a byproduct because it comes from air, not from fuel source. Okay, and then you have sulfur-based emissions based on how much of sulfur content you have fuel. As I said, the current sulfur level is very low, 10 ppm, ultra low sulfur. So sulfur oxides is not a major problem. And of course, if you use any additive, you will have combustion products of those additive. Lead oxide is shown here. Considering lead as one of the additive, which is avoided in the current fuel, gasoline fuel. We don't use lead to increase knocking quality. Okay, earlier it was used to increase knocking quality. Now it is not used because it's poisonous gas. So this is a quick summary of the primary pollutants. Okay, and the other species that are emitted from IC engine combustion. Okay. In the last class, we started our discussion on sources for pollutant formation. The way that we will move in this chapter is we have now understood the different types of pollutants, and we understood the health effects created by the pollutants. Now we are going to track, having understood the health effects of pollutant, we need to devise a suitable control strategy. That is what we are going to discuss in the next chapter. But before that, what we are going to look at, we are going to track the sources from where the pollutants are getting formed. We will, after tracking the sources, we will also discuss the mechanism upon which the pollutants are formed. When I say pollutant, our focus is only on these 4 species, which are designated as primary pollutants or regulated pollutants. They are also called as criteria pollutants. Okay, so after this, we will discuss a mechanism, and finally, we will also have a look at the various engine design or operating variable that influence the formation of these 4 species. Okay, this is where I stopped in the previous class. We are looking at the sources for pollutant formation in SI and CI engine. The sources are different. That's why we need to look at separately for SI engine and CI engine. Now we have started with this SI engine sources. Okay, SI engine have 3 primary pollutant. PM, particulate matter, is not there since we have a homogeneous combustion in SI engine. The 3 pollutants are NO, NO2 levels, as I said, less than 3%. That is also ignored. NO, SC, and CO are the 3 primary pollutants generated from SI engine. Here, during an engine operating cycle, we are looking at from where these pollutants are formed, at what time in an engine operating cycle these pollutants are getting formed. This is what we are looking at here. So, an engine operating cycle typically have intake, compression, then at the end of compression, you have combustion that will continue during expansion, a fraction of expansion period. The combustion process will continue to happen. Right after expansion, there is an exhaust. So among these different processes, intake is not a major, is not causing any pollutant formation, source for pollutant formation. But during compression, it provides a source for forming pollutants. Combustion, of course, will result in pollutant formation. And also during expansion and exhaust, there will be pollutant formation. So these period of time, during these processes, during this period of time in an engine operating cycle, the 3 species NO, SC, and CO are formed. Now let us look at this. During compression, the piston moves up, and what you have inside the cylinder above the piston, fuel-air mixture. So fuel-air mixture is compressed due to the upward movement of the piston during this process. Okay, so what is happening is when the piston moves up, and compresses fuel-air mixture, what do you have inside the engine? Carbon deposits, oil layers, lubricating oil layers, as well as carbon deposits which are soot of porous nature. You will have deposits, especially when you run the engine for a longer period of time over the metallic surfaces like piston, valves, okay, liner region. All this region will have deposits, carbon deposits. So you will have deposits, and you also have lubricating oil layers wherever you have a boundary. I mean, wherever you have a metal-to-metal contact, you need to provide a film, oil film, to reduce the friction. So you have deposits, you have film. When the piston moves up, it's going to compress a fuel-air mixture. What is happening due to the compression effect? A fraction of fuel will go and get locked in this deposits as well as in the oil layer. The oil layer and deposit, fuel will go and get trapped. Also, there is a crevice flow. We already discussed about what is this crevice flow, which is a radial clearance between piston outer surface and the liner. You have a small radial clearance to account for the thermal expansion of the piston. This radial clearance is enough to trap some fraction of the fuel mixture. Okay, so whatever there in the cylinder is going to get in through this radial clearance. What we are focusing now is how much of fuel is going into this, because fuel is becoming one of the source for unburned fuel is an important source for, unburned fuel trapped in the crevice will later on become an important source for HC emission. So the piston upward movement is allowing the fuel to get trapped in carbon deposits, oil layers, as well as some fraction of fuel goes into the crevice. It will go and get trapped. So the problem is the flame cannot reach this region. The flame cannot get access to the fuel trapped in carbon deposits or oil layer, or the flame cannot get access to the fuel that is locked in the crevice region, because flame cannot enter. meaning that this will become a source for HC emission. Since flame cannot enter, it cannot ignite the fuel air mixture prevailing in this region. Thus, it becomes one of the source for HC formation. Okay, so during compression, you have a source for HC formation because of these mechanisms. Okay, near the end of compression, you are discharging electric spark in the SI engine. Combustion gets started. Once combustion starts, there will be NO formation due to high temperature prevailing in the engine cylinder. One of the major source for forming NO is high temperature. I will discuss more about the NO formation mechanism later on, but just take a note that high temperature in the cylinder during combustion results in forming the NO, nitric oxide. Okay, and CO will also start to form during combustion because of oxygen deficiency. So wherever you have less oxygen based on the operating fee range, okay, if there is a less oxygen, you will have a CO formation. And this is happening during the combustion period. Okay, so when you talk about CO, there are two things. One is formation mechanism and other one is oxidation mechanism. Out of the total CO form, a fraction of CO will get oxidized in the cylinder itself. What I am saying is CO formed in the cylinder will also get oxidized to CO2 based on the oxidizing species available in the cylinder and based on the temperature. Temperature and oxidizing species will decide the rate of oxidation. Okay. Nevertheless, there is a formation mechanism, there is an oxidation mechanism. Whatever that comes out in the tailpipe is a net CO. Out of total CO form, a fraction of that get converted to CO2 in the cylinder itself. So during combustion, CO is forming and during combustion, SC will also form due to incomplete combustion. Sometimes you also have misfire. Okay, combustion event is completely missed. So that will become a source for unburned hydrocarbon in complete combustion. And during combustion also, the pressure in the cylinder is very high compared to the crevice region. So there will be crevice flow continue to happen during combustion also. A fraction of fuel air mixture will go and get into the crevice region. Okay, so you know the mechanism that drives crevice flow is delta P. During compression and combustion, the pressure in the cylinder is very high compared to the crevice region. That's why this delta P is what is causing the crevice flow of fuel air mixture into the crevice regions. Okay, after the combustion event will continue to happen and there is expansion followed by compression. Okay, during this expansion also combustion continue to happen. But during the expansion process, as you know, temperature will slowly drop. Temperature will start reducing inside the cylinder. Because of drop in temperature, the NO chemistry freeze. What do you mean by NO chemistry freeze?
There is no chemical kinetics related to NO formation.
Yeah. NO formation. So NO kinetics is going to stop because temperature is what you need to form NO. Since temperature drops after a threshold value, NO formation do not take place. This is what I mean by NO chemistry freeze. So NO will start forming during the expansion stroke. Later part of expansion stroke where the temperatures drop considerably. CO will also stop to form. CO chemistry will also freeze after NO chemistry freezes. Okay, CO formation also stops after some temperature drop. Also, to form CO, you need there should be an oxygen deficiency. Okay, so during later part of expansion stroke, there is no more CO formation, and then. During very late period of expansion, the crevice mixture will undergo backflow. What do you mean by that? So you have a pressure during later part of expansion stroke. The pressure here will be less compared to the pressure in the crevice region. If this is the case, then there will be backflow of crevice mixture into the engine cylinder. But this happens very late during the expansion stroke because you need this pressure to be lower compared to the pressure in the crevice region. This happens very late during the expansion stroke. Since the pressure and temperature in the cylinder is very low at the time where the crevice mixture flows back, that mixture cannot undergo combustion. So you know you need some minimum pressure and temperature to oxidize. Combustion is an oxidation reaction. So the hydrocarbon returning into the cylinder during later part cannot get oxidized because you don't have sufficient pressure or temperature inside the cylinder. Thus, it becomes source for HC formation. Okay, so after expansion, you have exhaust stroke. During exhaust, what is happening is whatever fuel mixture getting trapped in the carbon deposit or oil layer is going to be desorbed. What is desorption? So we discuss about adsorption. Initially, during compression, there is an adsorption of fuel in the oil layer and carbon deposit. Now we are talking about desorption. What is this?
Again, surface phenomenon, which is like a molecule is given back to the system.
It is reverse process. Okay, so during adsorption, the oil layer and carbon deposits are going to trap the fuel air mixture. That is adsorption. On the surface of carbon deposits and oil layer, you have a fraction of fuel getting adsorbed. Okay, that will prevail in the surface. When the pressure and temperature in the cylinder falls back very low, okay, this happens during exhaust stroke, the mixture that is adsorbed on the surface of carbon deposits in the oil layer is start to go back into the cylinder. This is called desorption process. And this desorption generally happen during the exhaust stroke. During exhaust stroke, the exhaust valve is open. Okay, since the exhaust valve is open at the time of desorption, so you have oil layers and you have deposits releasing HC. So HC is released during later part of exhaust stroke, where the pressure and temperature in the cylinder is considerably low and the exhaust valve is open. Okay, and the gas is leaving, exhaust gas is leaving. Whatever HC released from the carbon deposits or oil layers, so it is a desorption process. Okay, so there is a desorption. So when the HC is released, mixture, hydrocarbon fuel or mixture is released from oil layer and carbon deposits, the valve, exhaust valve is closed, it's open, the gases are leaving, exhaust gas is leaving the engine cylinder through the tailpipe. So this HC that is released from this deposits and oil layer will also be carried away with the exhaust gas. So you have exhaust gas carrying the unburned hydrocarbon through this tailpipe, and it is being discharged into surrounding ambience. Thus, it becomes one of the important source for HC emissions from the IC engines. Okay, so this is what is happening. This has become whatever we have discussed just now, or in a typical engine operating cycle, we consider these different processes and we have tracked the sources for these three emissions, pollutant emission, NO, HC and CO. To summarize, in spark ignited engine, you have these three pollutant, NO, CO and HC. Out of these three, NO and CO, NO is formed in high temperature burn gases and CO is formed in fuel rich zones where you have oxygen deficiency. Wherever you have oxygen deficiency, that is possible in the rich mixture, fuel rich mixture, you will have CO formation. Okay, fuel rich zones inside the combustion chamber result in CO formation. The other source for CO, even with lean mixture, if there is a dissociation reaction, what is dissociation? The carbon dioxide will dissociate. If there is sufficient temperature, this will dissociate and form CO. So this is again another source. Okay, one is oxygen deficiency, the other one is dissociation of CO2 in the engine cylinder. CO2 will dissociate and form CO, and this happens at somewhat higher temperature. Okay, but nevertheless, the point here to be noted is NO and CO are formed due to kinetics, chemical kinetics. The formation of NO and CO are primarily governed by chemical kinetic mechanism. Okay, CO with oxygen deficiency and dissociation, NO with high temperature burn gases. Okay, oxidation of atmospheric nitrogen is what is at high temperature is what is causing NO. So these two species formation mechanisms are primarily governed by the chemical kinetics inside the engine cylinder during the core combustion period. HC is a different pollutant. Okay, you could see that HC formation is not governed by kinetics primarily, Rather, it is governed by boundary layer fluid dynamics. Boundary layer fluid dynamics, we discussed different mechanism. If you look at crevice flow or adsorption in carbon deposits or oil layer, all these are in the boundary, in cylinder boundaries, right? So this HC formation is primarily governed by the flow of mixture, fuel air mixture into these regions which are located in the boundary. So we can say that HC formation is not controlled by kinetics, rather it is controlled by the boundary layer fluid dynamics. How the fluid flow happens in these boundaries is going to decide the concentration of HC in the engine exhaust. So we can, so you have crevice, you have adsorption, desorption. Another mechanism which we are going to discuss later on in detail is flame wall quenching. When the flame moves closer to the wall, it is going to get quenched because of heat loss effect. We already discussed about the condition for flame termination when we discuss SI engine combustion mechanism. Okay, please note that when we discuss about this mechanisms, emission pollutant mechanism, you have to recollect what we have discussed in the first module about the combustion event, because that is what is causing this pollutant formation. So when the flame goes very near to the valve in SI engine, you will have a considerably high heat loss. Considerably high heat loss will result in quenching of the flame. Flame will get extinguished. When the flame get extinguished, whatever fuel air mixture located in the wall region, cylinder wall region, so you have a layer of fuel air mixture located in the cylinder wall region that won't get ignited because the flame is quenched. Nearer to the wall, the flame is quenched, meaning that the flame doesn't ignite the mixture located around the wall region. Okay, this is another mechanism for HC formation. And then bulk quenching, I will give more details later on. Bulk quenching is about quenching of the flame in the cylinder core region itself. Flame quenching, flame wall quenching is a quenching of flame near the wall. Bulk quenching happens in the core region, core cylinder region. Okay, sometime under certain conditions, under transient engine operating condition, when the temperature falls suddenly, the flame cannot be maintained. Stable flame cannot be maintained. The flame will get extinguished. This is what I mean by bulk quenching. This is also a source for misfire and forming HC. And overall, if you look at the sources for HC, they are formed primarily due to the boundary layer fluid dynamics, whereas NO and CO are formed due to kinetics, chemical kinetics. So having understood the sources, now we are going to look at important plot with respect to these three pollutant formation. You could see that this plot is drawn by taking NO, HC and CO in y-axis and phi in x-axis. What is phi? Phi is equivalence ratio. And here I have marked the stoichiometric. Stoichiometry is 1, and in this region you have phi less than 1, which is lean mixture. In this region, right towards right, phi is greater than 1, it's a rich mixture, and 1 is a stoichiometric mixture. So what we are looking at here is, we are looking at how the equivalence ratio affect NO, HC and CO values in SI engine, because in SI engine, the NO, HC and CO are influenced more by this VLR equivalence ratio. Later on, we will discuss about all the parameters that influence pollutant. One of the important parameters that influence this three pollutant in SI engine is the equivalence ratio. That's why we are looking at the trend of this three pollutant emission with respect to equivalence ratio variation. So what you can observe is, you could see that when you move towards stoichiometry and rich mixture, NO initially increase, reaches a max value, and then start to drop. So in a lean region, very lean or very rich region, NO values are very low. What could be the reason? So this is too rich, this is too lean. In this region, NO concentration is very low.
Temperature, sir. In cylinder temperature.
In cylinder temperature. So just now we discussed that NO formation is sensitive to temperature. When the mixture is too rich, you have incomplete combustion. Okay, that's why HC and CO are shooting up. You could see that they are rising sharply due to incomplete combustion. So combustion is not perfect, and temperatures are less, so NO is less. When it is too lean, you are burning less fuel. So there is a less thermal energy release, lower temperature, NO is less. Somewhere you could see, when you track the peak value, when it is happening, peak value is happening with a slightly lean mixture. So you could see that with a slightly lean mixture, the peak NO value is happening. Now I have a question to you. You know that with slightly rich mixture, temperatures are high, but NO is not peaking up at that high temperature phi value. Rather, it is peaking up at a slightly lean phi value. What could be the possible cause?
Sir, one thing that comes to our mind is that at slightly lean mixture, even the temperature is not so high like 1.1 or between 1 to 1.1, but the oxygen availability will be very high. And
Yeah.
NOx formation is the function of oxygen availability plus temperature.
Yeah.
So temperature and like a certain amount of certain level of temperature plus oxygen availability will peak the NOx. Hence, it is peaking at slightly lean.
Perfect. This is a perfect answer. So you have a slightly lean mixture. In this slightly lean mixture, temperature will be high, oxygen availability is also high. So you have more NO formation happening with a slightly lean mixture. With a slightly rich mixture, the temperature will be high, but oxygen availability is less. Due to less oxygen, I am talking in a relative sense. Okay, with a slightly rich mixture, you know oxygen is less in a relative sense. Because of that, NO doesn't peak with a slightly rich mixture where the temperatures are high. Rather, it peaks with slightly lean mixture where the temperatures are high. Oxygen is also available. Okay. The rest of the phi values, it is less. And the HC, if you look at the trend, up to certain lean value, the HC drops considerably when you move from rich towards lean. Up to certain phi value, say around 0.8 or so, you have a drop in HC, considerable drop in HC. But when you move towards further lean, you could see that HC is increasing in this. So what could be the possible cause for the increase in HC in the lean region lower than 0.8?
Sir, it could be like a bad combustion or a misfire or something like that.
Misfire, exactly. So this is misfire region. So you should always remember that SI engine combustion is a flame stability based combustion. When you move towards lean mixture, the problem is the flame stability is poor. So you have a poor flame stability in the lean regions. When I say poor flame stability, what I mean here is you are not able to maintain a stable flame. When you are not able to maintain a stable flame, there will be ignition problem. Okay, the worst case scenario is misfire, wherein the combustion few cycles completely miss the combustion event because you don't have stable flame stability, flame cannot sustain. Okay, there is no more flame and combustion event is completely missed. So you will have few misfire cycles which are quite possible in the lean domain. That's why you have a sharp rise in HC when you drop phi value below 0.8. This is the reason why we have a very narrow operating phi value for SI engine. What is the operating phi value we discussed?
0.8 to 1.1, 1.2.
Yeah, 1.1. Sometimes we also go towards 1.2, but this is a general operating regime. Okay, general operating regime, because you will have a problem of maintaining stable flame when you move towards very rich or very lean. Okay, especially with very lean mixture, you will have a very poor stability. SC will shoot up, as you could see here. There will be sharp rise, slope start rising up, slope start increasing considerably when you move towards lean below 0.8. Okay, CO drops continuously, as you could see here from rich towards lean. CO drops continuously because you have sufficient oxygen available, and there is a considerable drop in CO value when you move towards a lean mixture. So overall, you could see that there is a trade-off here. Towards lean, you can control SC and CO if you are able to run lean. But the problem is, if I move in this direction, SC may shoot up beyond certain phi value due to misfire, right? And the other problem is the flame stability. Okay, you cannot maintain a stable combustion, stable flame when you move towards lean. Okay, So with a lean mixture, SC and CO are under check, but you could see that NO is considerably high. Okay, so there is a trade-off here. When you move towards lean, you can control SC and CO, but generally you work in this operating regime because of poor flame stability with a lean mixture. Okay, that's why you operate in this regime. In this regime, you could see that NO is very high. Within the operating fee range of SI engine, you could observe that the NO values are very high. SC and CO are also high. That's why you need to control using some mechanism. You need to control these pollutants. Okay, simultaneously you cannot reduce all the three pollutants in SI engine. Okay, because of the restriction in terms of maintaining a stable flame. Clear?
Clear, sir.
Okay. Okay, so far we discussed the sources for pollutant formation in spark ignited engine. Now we are going to look at the sources for pollutant formation in diesel engine, compression ignited engine. Okay, in compression ignited engine, you know you have 4 pollutants. Unlike SI engine, you have SE, CO, NOx. In NOx, you cannot ignore NO2. Here you have NO and NO2, and NO2 can go up to 30%. In SI engine, we generally ignore NO2 because it's less than 3%. Okay, NO is a primary component in NOx. So here you have NO2 also, NO, SCCO, and then more importantly, you have this particulate emissions. So you have more number of primary pollutants in a diesel engine. That's why pollutant control is in fact relatively complex for diesel engine compared to SI engine. Okay, you have more number of species, primary pollutant species to be controlled. So that's why we need to spend more money. Okay, there is a considerable cost involved in controlling these 4 species within the current emission mandate. Okay, so there are a lot of, later on I will discuss about in-cylinder control and after treatment control. You could see that you have to go with a combined in-cylinder and after treatment. In fact, in after treatment, you have to go with more than one device, one after treatment device to control these species, different species, which is not the case with an SI engine. Later on, I will discuss about that. With one device, you can control the primary pollutants in SI engine, but you cannot do that in diesel engine. You have to use more number of devices to control the pollutant. So pollutant control in a diesel engine is complex, and also it involves higher cost compared to SI engine. This is an important point to note down. Now let us track the sources for pollutant formation. So you know, in a diesel engine, we are injecting fuel near the end of compression stroke. Typical injection timing I have already discussed, 20 degree, around 20 degree before TDC is what is the fuel injection time. And with a very small ignition delay time will be few crank angle degree. That few crank angle degree is what is available for mixing fuel and air. We can call it as pre-mixing. Pre-mixing is nothing but the fuel air mixture that is prepared before the start of combustion. That is what is the pre-mixing. The mixture that is pre-mixed before start of combustion is considerably low in a diesel engine, right? Because you are giving very few crank angle degree. In SI engine, what is the time available for mixing?
Complete suction and compression that way.
Exactly. So approximately you have entire intake and entire compression stroke. What is the crank angle duration for one stroke in a 4-stroke engine?
So 180, na?
180. One stroke is 180 degree for 4-stroke. So in SI engine, you have 180 plus 180, 360 degree crank angle is a typical time available for pre-mixing. Whereas in a diesel engine, very few crank angle degree, because you are injecting fuel at 20 degree BTDC with a small ignition delay time. Okay, you are going to start the combustion event. So the fuel air pre-mixing is very poor in a diesel engine because of this. Due to this poor pre-mixing, you end up in forming heterogeneous mixture, fuel air mixture. Heterogeneous means you have a different equivalence ratio inside the cylinder. At different locations, you will have different equivalence ratio. This is what I mean by heterogeneous mixture. So with respect to space inside the cylinder, that is from one location to other location, with respect to time, the mixture proportion in the cylinder is different. So we have a non-uniform mixture distribution inside the cylinder of a diesel engine. This is one of the important factor that influences all these 4 pollutant formation. You have a non-uniform fuel air mixture distribution, okay, due to limited time available for mixing. Okay, so you have a non-uniform mixture distribution. This non-uniform mixture distribution is one of the major factors that affect all the 4 pollutants. So later on, I will give more details as we move on. Okay, but just take a note here that we have a limited time for mixing. We end up in creating a heterogeneous mixture. There is a non-uniform mixture distribution. Pollutant formation is dependent primarily on how the mixture distribution happens with respect to time. This is one of the major deciding factor. NO forms, when you track the sources, NO forms in high temperature burn gases similar to what we have discussed for SI engine. Here also high temperature burn gas is one of the important source for forming NO, but the difference here is we have a heterogeneous mixture, unlike SI engine wherein we have a homogeneous mixture. That is the difference here. But the mechanism is same. Wherever you have a high temperature burn gas, you are going to get the NO formation kinetics happening in that region. CO, similar to SI engine, here wherever you have a deficiency of oxygen, CO is going to form. CO, partial oxidation of carbon in the fuel is what is causing CO. Partial oxidation of carbon in the fuel is primarily due to less oxygen available in the cylinder. Less oxygen is because of non-uniform mixture distribution, as I just now said. So you have local fuel-rich region that will cause CO formation in diesel engine. HC formation is slightly different from what we have discussed in SI engine. So HC sources are different, as you could look at here. I will give more detail as we move on. So the formation sources are primarily mixing-based sources, as you could look at. There are overlean region. So what is overlean and how these overlean regions are created? These overlean regions are created due to too much of mixing. There are locations inside the cylinder wherein there is too much of mixing, and because of that you will have a considerably high air proportion, very less fuel proportion. This is what I mean by overlean region. So it is below the flammability limit. You know, fuel air mixture cannot ignite at all possible combination. You have a finite value of fuel air mixture that can ignite, that is called ignitable range. When you mix too much, you will end up in forming overlean regions inside the cylinder. That becomes one of the source for HC formation. This is due to over mixing. The other source is under mixing, just opposite to what we have discussed. There are regions inside the cylinder where you have considerably high fuel proportion, very less air proportion, because air is not mixed well with the fuel. So you have considerably high fuel proportion, less air proportion. This is what I mean by under mixing. You are not mixed well air with the fuel. This is what is causing under mixing. Under mixing means you have a rich fee that cannot ignite. Again, it is beyond the flammability limit. You have a narrow fee value, ignitable range. Due to over mixing or under mixing, you are moving out of the ignitable range, and this results in HC formation. Other source is spray impingement on the cylinder wall. When you spray fuel into the engine cylinder, a fraction of the fuel may go and reach the wall. Wall region, you know, cylinder wall is a cooler region in the combustion chamber. This fuel that reaches wall will form a film, and this film will slowly oxidize and become source for HC formation. This is considerably severe in small bore diesel engine because spray can go and hit the wall. I'll give more detail in the next class because of lack of time. And the next source is nozzle sac volume. Nozzle sac volume is the volume, small volume that is provided at the end of fuel injector, and this is this provides a surface for measuring orifices. Okay, so it's a circular surface at the end of needle. Injector needle, you have a small circular surface you could look at here, and this surface is provided to measure the orifices. You will have n number of orifices around the circumference of the sac volume through which you are spraying the fuel. This is one of the source because the fuel get collected here and later on goes into the cylinder at a very slow velocity, and this becomes a source for HC. Okay, I will give more detail about this last two mechanisms in the next class. It's time up. I stop here. If you have any questions, you can ask.
Sir, one question.
Yeah.
Sir, actually, we know that like with rich mixture, the combustion temperature increases. But one thing what we see is with richening the mixture, we are able to see the exhaust temperature comes down. So how these two are happening, sir?
No, rich mixture, so again, rich is a qualitative term, right? You have to look at the actual phi value. So when it is too rich, the combustion is poor, right? You will have deteriorated combustion when the mixture is too rich. The combustion, what I mean to say here is incomplete combustion increases when phi value increases. Incomplete combustion means you have less temperature.
Yes, sir. Actually, when we are doing calibration on the engine here, when we maintain equivalence ratio of say 1.0102 also, our exhaust temperature starts coming down compared to ratio of 1. Just trying to understand how that can happen.
Okay. So you are talking about exhaust temperature. You are saying that with rich mixture, the operating temperatures are high. Why exhaust temperature is low? Is that what you
Yes,
are
sir.
asking?
Yes, sir. Yes, sir.
You should not relate exhaust temperature directly with the phi value because exhaust temperature is a cumulative effect of several factors. For example, combustion phasing. If you have a late combustion phasing, if you have a late burning, exhaust temperature is going to be high, but work extracted from the engine will be less. Did you get what I am saying? Exhaust temperature is not only a function of operating phi, it's a function of several other factors. One of the important factor is combustion phasing.
Okay.
Combustion phasing means when the peak pressure is happening. When it happens at appropriate time, you will extract more work from the in-cylinder thermal energy. When it happens late, you won't be able to extract more work from the in-cylinder thermal energy. So you mean to say that you are releasing more energy into the exhaust. Exhaust temperature will be high.
Okay, sir.
Operating phi alone cannot decide exhaust temperature. In fact, it is more sensitive to the combustion phasing. With the delayed phasing, you will have high exhaust temperature even with the phi value lean.
Okay, sir. Thank you.
Operating phi value will affect in-cylinder temperature. Perfect. This is what we also discussed. But what I am saying here is when based on the combustion phasing, when the peak pressure is happening and so on, the work extracted from the combustion energy release is going to be different. That will reflect directly in the exhaust gas temperature.
Okay, sir. Thank you.
So delayed phasing means you want to say advanced, right, Nasir, if I'm not wrong?
Can you say it again?
So delayed phasing means you want to say about advanced timing, right, Nasir?
No. Delayed phasing is delayed timing. So I'm talking about, suppose if you have a TDC here, okay, so the combustion pressure can peak. So this is normal. When you have a delayed combustion, you could see that this is a delayed phasing. With delayed phasing, you are not recovering the work from the combustion energy release well because you have lack of time. So the energy that is let out into exhaust will be very high in this case compared to this case. Did you get what I am saying?
Yes, sir. So this type of phasing in SI engine probably can be achieved with retard of spark.
Yeah, you need to control spark timing. So this is primarily controlled by ST, spark timing, delayed or advanced. So
Thank
you have to phase it properly by controlling spark timing. This is what I'm saying. This is very important because you have to extract maximum work in the cylinder. Otherwise, your thermal efficiency, your power and torque will drop. You are burning more fuel, but you are not recovering well into work in terms of work. You are releasing all those into the considerable fraction of those released in the cylinder into the exhaust gas. Exhaust gas will carry more thermal energy with a delayed phasing.
Thank you, sir. Thank you so much, sir.
Yeah, okay.
Yeah, hi sir, Vijay here.
Yes.
Sir, this assignment, I have replied to that assignment 2 mail. Like I have again forwarded to your S mail account. Sir.
Okay, I will look at it. I have not received, that's why I sent an email. I will, if you have sent
I
it
have
again.
forwarded now, sir. Thank you, sir.
Okay. Okay, I'll stop here. I will see you tomorrow at 6 o'clock. Thank you.
Thank you so
you,
much,
sir.
sir.
Yeah.
Thank you, sir.
Thank you. Bye.